Okay, welcome to part 4 of our interactive plots section. So we're going to pick up with some fancier plot types that we maybe haven't seen before and how we can construct them in Plotly, right? The goal is to give us lots and lots of options so that when it comes time to work on our project, we have some non-standard plot types in our tool belt that we can go to. So the first one that I'm going to show you is going to be a 2D histogram, which is for numeric data, which is like the numeric analog to a heat map. So it's very similar to the hex map that we showed earlier. So to build this one, super easy. We can just take our diamonds data and pipe that to Plotly, and we'll look at the x being the log of caret and y as the log of price. So we saw this same exact plot with the hexagonal heat map. And then now we're going to look at it slightly differently with the add histogram 2D. And we'll see what this looks like. So now we get a similar pattern, except it fills in colors for the entire map, not just where there is data. So the colored spots are where there are data. And then out here we have 0 data, but it still gets colored because it is doing the kind of a 2D version of a histogram. So imagine these columns, these Z values coming out at the top, but instead with 3 dimensions, they're doing it by color. So that's how a 2D histogram works. It's just like the version of a heat map, where instead now we have numeric variables. So this same type of plot can be used for what's called a correlation plot. So a correlation plot is a statistical plot that uses the correlations between each pair of numeric variables and visualizes them to show us which ones are very strongly related versus not. So to do this with a static version, we can essentially turn our correlation matrix into a visual by using a function from the core plot package. And the function is just core plot itself. So core plot, we can run this. And this gives us a visual representation of this correlation matrix. So we see that price and caret are very related positively. X and caret are very related positively. Less so for price and table, and negligible for price and depth. But we're left to rely on kind of our own interpretation of the color and of the size of the circle in order to interpret what exactly these values are from the correlation matrix. So one thing that we could do is convert this into a interactive heat map where we can mouse over and get the exact value. So kind of getting the best of both worlds. We're getting the visual elements from the color, but also the numeric values from the interactivity. So I already have this coded up for us, but essentially what we do is we take the correlation matrix, which is CORR. So all I did was look at the numeric variables in Diamond's data set and passed it to the COR function, which calculates that first correlation matrix that I showed. So we take that result, we turn it into a data frame, which Plotly needs. And then our x-axis is going to be the variable names. Y-axis is going to be the variable names as well. And the z, which is going to be interpreted as the color, is going to be the correlation when we use add heat map. So add heat map means that we've already done the correlation calculations beforehand. It's kind of like the analog of add bars where we did the binning beforehand ourselves. But now with add heat map, I specify what that Z value is, and then we give it the color scale. And then to make it statistically accurate, what we do is we vary the colors from -1, so a negative perfect correlation, all the way up to a positive perfect correlation. So when I run this, this gives us a kind of rotated version of this correlation plot. So now when I mouse over, I could clean up what the mouse over text is, but I get the correlation as well as the color effect of the different correlations for this set of variables. So a neat little application that we can kind of just copy and apply to whatever data that we're working with. So here is an exercise for you to try with heat maps and those 2D histograms. So next up is going to be a slope graph and dumbbell charts. So these plots are used to display numeric variables for different groups. And slope graphs are a very minimal way to show change across categories or change across time points. So here's an example of a slope graph. So this slope graph is displaying the time plot, in essence, of the average life expectancy for countries within each continent from 1952 to 2007, and it's skipping all of the middle years. So it's just showing the very beginning and the very end. So we're just getting a big picture view of the total change through time for these countries within the continents. So that's what a slope graph does. And it's very easy to see the change based on how steep the slope is, and there's no negative ones, but we could really see the direction easily, especially if there was a negative life expectancy decrease. That would pop out really, really well with this type of graph. And if I wanted to create this during ggplot, create this for ggplot, here is the code that we would do. So I'll just kind of copy this and run it in the console. So what we're doing is we're just looking at the minimum year and the maximum year, and then we are averaging over all of the countries within the continent for these 2 years. And then we need wide data. So I need one column for 1957. I need another column for 2007 or 1952, excuse me. And then we pass it to ggplot. We create the segments, so that's going to be the lines here. And then we add the text, which is going to be the beginning text here. And then we add some labels and then clean up the axes a bit. So that is what this plot does. So let's take a look at this result. And notice here in ggplot, it doesn't look as good because that original plot was made with a package called, let me find it here, slope graph 2. So slope graph package with the gg slope graph 2 function. So ggplot has a lot of extension packages that extend the capabilities for certain types of plots. So this is an example of one of those. So for slope graphs, this would be a great way for you to create a static slope graph. So here is the code if you want to try to do that on your own. But ggplotly doesn't work too well with these extension plots. Some of them, yes, but a lot of them, no. So if we want to add interactivity to this, we have to recreate this ourselves using Plotly. So let's see how we can do that. So that is what we're going to do in the code here. So the first thing I'm going to do is comment out all this stuff down here real quick. And we have the data transformations. So the first thing that I'm doing is summarizing by average life expectancy for each continent, and then I just convert it to wide data because I need 2 separate columns. So I'm left with a wide data set, 2 columns for the years 2007 and 1952. So then here comes the Plotly code. So what we want to do is first pass this to the Plotly function. So recreating the slope graph, we take that wide data and we're going to first add in these segments. And we're going to start our axes at 1. So this axis, the 1952, will be 1. This axis will be 2 for 2007. So we're going to start our x at 1, and we're going to end the x using xend at 2. And then we are going to do the same thing for y. So now we're going to start our y at 1952, and end the y at 2007. So we can take our y and start it at year 1952 is what we named it down here. And then we can end the y at year 2007. I forgot to add plotly function. So here are our segments. So we have the segments now. So next up, we want to add in the annotations. So to do that, we can use the add annotations function, and we're going to offset it a little bit. So I want it to be a little bit before this x-axis of 1. So x equals 0.95. And we want the y to be, for the left side, we want the y to be at year 1952. And then we want the text to be equal, we'll keep it simple. We'll just do a paste, continent, year equals 1952. So that gives us this. So this added the continent and the year in which the average life expectancy was calculated. If I want to get rid of those arrows, I can add the argument show arrows, show arrow equals false, and that will get rid of the arrows. If I want to get the annotations on the right-hand side as well, let me change this. So I had just the constant 1952. We want to get the actual life expectancy for that. So if we want to get the annotations on the right-hand side, we can just copy that same code and add our annotations. Now it's going to be offset a little bit above 2, so 2.05, and we'll change it to 2007. 2007. There we go. And then if I wanted to clean it up a little bit, here's where I can add in the layout features that I have already coded for us. So I'll just uncomment these real quick. So all these are doing are cleaning up the axes a bit and putting in the years and getting rid of the grid lines. That is what this is doing. So notice that the interactive features here don't really add anything else to this plot, right? I already have the labels. I already have what country, what continent, and what value this is. So just because I can make something interactive doesn't mean I should make it interactive. So this was just kind of demonstrating how I can make this type of plot, because we're going to use a similar strategy in the dumbbell chart, which is shown next. So a dumbbell chart is going to be a type of plot that looks like this down here. And what that does is a kind of simpler version of a slope graph, but not quite as general. So that's why it's a bit simpler. So they're typically used to compare two different classes, so two groups for numeric values. Whereas a slope graph, we can kind of extend this. So imagine I had another year, and another year. I could keep going with this slope graph. But dumbbell charts are going to just be used for two different groups or two different categories for a numeric metric, or two numeric metrics across time. So we are going to recreate this plot that was made with ggplotly, or that was made with ggplot with Plotly. So what's going on here is we're taking our MPG data, which are miles per gallon. So it has a sample of a bunch of different cars and the year, make, and model, and the city and highway gas mileage for all of them. So what we can do is we're going to summarize this data. We're going to calculate the mean city and the mean highway miles per gallon for each type of car. And then we are just going to order them using that same factor reorder strategy so that they are going to be in increasing order. So it doesn't change the data, it just changes the attributes of these factors, or for the model factor. So that is the first preliminary data manipulations that we need to do. Next, to create this plot. So interactivity would be nice because now I'm kind of having to rely, especially on these upper ones, I'm kind of having to read all the way down, figure out and kind of guess where exactly these MPG lies. So interactive, if I mouse over, right, that would be a nice feature to have. So that's what we can do. So let's go ahead and pipe this to our plotly function. And the first thing that we'll do is add in our segments. So add segments, we're going to start at, looks like we started at the city and we end at the highway, and the Y value corresponds to the model. So the Y doesn't have to be numeric, it can be a factor variable. So the start is going to be, X is going to be CTY for a city, gas mileage. The X end is going to be highway. Y is going to start at model, and it's going to be a constant horizontal line, so it's also going to end at model. So the same arguments as the segments for the slope graph. And then it looks like they're all a constant color. So we can do color equals identity gray. There we go. So now we have all of our segments. So now all we have to do is add the dots on the beginning and end. So to do that, we can use add markers. And we'll start with the city on the left. So X is equal to CTY. Y is equal to model. And it looks like we put a constant color in there. So color is equal to identity blue. And I need to pipe it. There we go. So notice here the traces that I get. So if I want to rename these, I can use the name argument. So rather than calling the markers trace 1, I can do name equals city. And that changes it to city. And I can get rid of trace. So I don't really need a legend for the segment. So I can use show legend equals false. And that gets rid of that. Now I just need to copy this to add in our markers for the highway. So HWY changes to highway. And we'll make this orange. And there we go. There is our nearly completed dumbbell chart. Only thing that we can do to improve this is we could add a title, but we could also change this so it's not just referring to the city miles per gallon, because both the highway is on there as well. So to change the x-axis title, we can do layout x-axis, and we have to put it in a list. And again, I just found that out by Googling. So we have to change the x-axis title. So now it says MPG. And there is our completed dumbbell plot. So this gives us a neat interactive and really visualizes that the Civic, and it doesn't show all of them, so some of the labels are cut off a bit, but the Corolla is going to be the best one, and it also has the largest increase between one of the larger increases between the city and the highway in terms of MPG, and it has the best of each of them. So pretty neat plot to show numeric distributions across different groups. So here is an exercise for you guys to try. Instead of creating a slope graph for the Gapminder data, see if you can create in part B here a dumbbell plot using the Gapminder data, and then reverse, so then we can do a slope graph for the MPG. So the last type of plot that we're going to learn is going to be a parallel coordinates plot. So this is going to be a way to show higher dimensional data. So generally speaking, with two-dimensional data for numeric, we can use scatterplot, right? An X and a Y variable. For two numeric variables by group or by time, we can facet. So I could have a panel for each different group and have a scatter plot on each of those panels. I can use a slope graph or a dumbbell plot like we just saw. Or I can have, for three numeric dimensions, with our Gapminder, I can use a bubble plot, incorporating that third dimension via size. For more than three numeric dimensions, a good plot that we can use is this parallel coordinates plot. So this is going to be a multivariate display that organizes many numeric axes in parallel rather than orthogonal like your typical XY coordinate plane. And its effectiveness depends on how grouped data behaves across variables. And what we do is we look at the profile. So we look at the profile of each observation across these many numeric dimensions, and we connect the dots. So we have the iris data here. One of those ggplot extension packages is called ggparaccord. So ggparaccord for parallel coordinates plot. And this is what the output is. So this is a standard parallel coordinates plot. So we are looking at each line represents a single flower, and we're looking at the values across 4 different axes. So 4 different numeric distributions that we are showing here on the same plot. And grouped data, so we're looking at the species. So we can really tell that these profiles are different based on the species. So a parallel coordinate plot is really illuminating in terms of the information that it shows about these different groups. And there is 3 things that we're looking for in a parallel coordinates plot. So the first one is there clusters by color? So if I look at each of these different axes, we can definitely tell that the petal length and petal width are definitely grouped by the species. So they behave differently for each of the different species. That's what we're looking for. Less so for sepal length and less so for sepal width, right? They're kind of more mixed, but they still have a kind of general profile for each species. Then we're also looking at, like, all those lines parallel, are they behaving the same? Are there certain ones that are not following the trend, right? Maybe there was one setosa flower that went really high up in the petal width and then really far back down, right? That would be kind of an anomaly. So those are the ideas that we're looking for with those individual lines and the colors. We're also looking at the slopes of the lines. And this gets us an idea at the correlation between numeric variables. So if the lines are relatively flat, that indicates a positive correlation. We're at low values corresponding to low values, high values corresponding to high values. And we can confirm this with the correlation matrix that I have shown here. So we should see relatively flat trends between petal length and petal width. So we should expect a positive correlation. So petal length and petal width, really strong positive correlation. Perfect. When we have this kind of mismatch where high values are corresponding to low values are corresponding to high values, that's when we get a negative correlation. So if we were to look at sepal length and sepal width, we do see that negative correlation. And the more kind of spread out they are like this, the weaker that correlation is. So that would give us a correlation closer to 0. So that's how we're interpreting the slopes of those lines. Then we're also looking at the spread by the color. So for each group, how spread out are they on each variable? So for petal length, right, they are very, very close for the setosa, whereas for sepal width, they are a lot more spread out. So those are all the different things that we can look at a parallel coordinates plot. Okay, so like I said, this was created from the ggally package in the ggparcoord function. And one important argument is the scale. So when we're visualizing so many dimensions on the same thing, imagine one value was from 0 to 1, and the next one's from 1 to 100, the next one's from 1 to 1,000. Right, the scale is going to really impact how this final visual looks. So we need to kind of standardize our scale. And that's what the scale argument does. So one way that we can do that is by converting into a z-score. So a z-score is going to be x minus x bar over the standard deviation. So that puts the mean at 0 and the standard deviation at 1. So typically values will be between -3 and +3 standard deviations away. But with outliers, or if there's a strong skew, we could get up to 4 and 5. Another common way that we can do this is by the uni-min-max transformation, which puts everything on a 0 to 1 scale. And what that does is it keeps the relative position of all the values the same. It just puts them on a common scale, 0 to 1. So that's what we have here. So this is the one that we are going to use to reintroduce this via Plotly. So let's see how we can do this with Plotly. So the first thing that we need to do is redo those. We have to manually do the transformation ourselves. So we have to convert all of these to the uni-min-max scale. So to do that, we can take our iris, and to change the values of the data, we're going to use a mutate function. And I want to do this across all of the numeric variables. And the function that we're going to use is from the scales package. We've seen that before. Rescale function. So this does the uni-min-max transformation. So if I just look at that, now everything is on a 0 to 1 scale. So if we take a look at the specific transformation here, the maximum value is a 1, and the minimum value is going to be a 0, and everything else is in between. So then we can pipe that. We actually need a value to group by. So remember, in order to get a line for every single group that we want, we need to group by that variable. So we actually want to just group by the observation. So to get that observation ID into the data, we can use the Tibble function row ID to column. And we are going to call it the variable obs. So all that does is give us the row ID. Now I can group by this value after I convert it to long data. So we actually need long data in order for us to make the parallel coordinates plot. So we're going to do pivot longer, calls equals everything other than species and observation, which are our indicators. And we're going to put the names to variable. So we're going to have one column that's variable, and it will give us either sepal length, sepal width, petal length, petal width. And then the next column will actually give us the values of those particular variables. So now we have tall data, long data, which is what we need. Next up, we can group by the observation, which we need to do in order to get a line for every single observation. Now we can finally use our plotly function, and our x is going to be variable. Our y is going to be value, and we're going to color by species. And then we specifically want to add lines. We can use add lines. And to make the lines blend in a little bit so they don't overlap each other, we can use alpha equals 0.5. And there we go. Here is our parallel coordinates plot. So with this, we have a different color scheme than the paracoords function, but this gives us the parallel coordinates plot for the iris data. So this can be very helpful for visualizing high dimensional data. So in the next optional video, we will look at graphical queries and how to recreate these goal plots from the very beginning. So I will see you hopefully in the next video.